Previously, we have discussed several aspects of numerical method. First, we have talked about what we exactly do when we apply numerical methods for problem solving, and then we have established that the problems we solve in numerical methods, they usually come from physical phenomena. We discussed how to model a physical phenomena and then how to solve those model equations, and we have seen that usually solution of those model equations involve numerical methods. Now all these previous lectures together, they completes the introductory phase of our course, and now we are really getting into the numerical methods of different kinds. And first we'll start from root finding, which means that we'll study the solution of equation consisting only one unknown. And first we'll look at a method that we call bisection method. So in bisection method, what we do is that for solving fx equals 0, we start by identifying an interval around the solution. For example, this is the initial interval around the solution. And then our goal will be to narrow down this interval iteratively to get the solution. So let us see how we can solve algebraic equation of one unknown using bisection method. We take an algebraic equation, and by algebraic, again and again using this term, what we mean that we are not talking about differential or integral equations. We'll come to differential equations later on, but right now we are not talking about them. We are only considering now algebraic equation of one unknown. And such equations in general can be written as fx equals 0, where x is the unknown. Such equations we call linear if they are of the type of ax equal plus b. Here a and b are known constants, so ax equals b equals 0. If that is the equation, then we can solve this equation very easily analytically. For a not equal to 0, we know that the equation gives us a solution of x equals minus b by a, so it's very easy, and there is no question of using numerical methods for such cases. However, if the equation is not of this type, then the equation is called nonlinear. Now nonlinearity comes from various terms, such as in a nonlinear equation you can get sin x, cos x, log of x, etc., etc. You will get x to the power n, where n is neither 0 nor 1. That means in your equation you may get x square, x cube, root over x, etc., etc. So when you get some of this kind of terms in your equation, then your equation is definitely nonlinear in nature. If you plot this fx equals x plus b, you get a straight line. But if you plot any such equation where you have such terms, you don't get a straight line. You get some kind of a nonlinear curve. Now we wish to solve this nonlinear equations. Now how do we solve these nonlinear equations? Sometimes we have nonlinear equations where we can have the solution analytically. For example, if we have a quadratic equation, we know how to solve a quadratic equation analytically. But most nonlinear equations cannot be solved analytically. For example, if I have an equation x plus tan x equals 2, this cannot be solved analytically. This is a nonlinear equation and we have to use some numerical method to solve it. Here our focus is a nonlinear equation of one unknown, and such equation is written in general fx equals 0. There are fundamentally two approaches of solving such equation. In first approach, we start with an interval x1, x2, and the solution we know that falls between x1 and x2. Once this x1 and x2 are identified, subsequently what we do is that we iteratively close this gap. So our goal is to reduce this x1 minus x2, that means bringing x1 and x2 closer and closer iteratively. And eventually we will come very close to this solution where we will terminate our calculation and we will assume that we have reached the solution. This is a kind of technique that we call bisection. There are other techniques also, they follow the same type of procedure, same philosophy of procedure, but we will look at one of them, that is bisection. The other approach is that we can solve linear equations, so we linearize the nonlinear equation, and how we do so we will look into it, and this linearized equation we solve it. But linearized equation is not the actual equation, so what happens that is not the correct solution, so we iteratively update this linearized solution. It doesn't seem very easy now, but you will see this is an easy procedure and we will see it in subsequent lecture. This kind of procedure is something that we call a Newton-Raphson type method, and we'll talk about Newton-Raphson in subsequent lecture. Right now let's discuss bisection method. So let us see how we can solve the equation fx equals 0 using bisection method. This is a function y equals fx. If I plot it, it shows it like this blue curve. It is not necessary to plot it to solve fx equals 0 using bisection method, but this kind of a pictorial description will help us to understand how does this method work. So what we do is that we first, here in this case, we know that fx equals 0 give the exact solution. We don't know the exact solution, but let us say that if we have the exact solution, then that will be at this fx equals 0. So at this particular point where this blue curve cuts the x-axis, that would be the point, that would be the x location. If I take the x location, that would be the root of this equation. Now if I go toward right side, then I see that my fx is greater than 0. If I go toward left side, then I see that my fx is less than 0, and exactly at this point, at this root, fx is equal to 0. Of course, depending upon the nature of this curve, it may so happen that right side is less than 0 and left side is greater than 0. That may so happen. But the main point here is that the root comes at fx equal to 0, and one side of the root will be fx greater than 0, which eventually is the right side here, and another side of root is fx less than 0, which incidentally is the left side here. So now what we do is that we take some trial, and from our trial we identify 2 points. One is x1 and another is x2, such that f of x1 multiplied by f of x2 less than 0. What does that mean? Well, if f of x1 and f of x2 individually both are less than 0, that means both of them will be on this side, then of course their multiplication cannot be less than 0. Their multiplication will be greater than 0 if individually both of them are less than 0. On the other hand, if f of x1 and f of x2 both are in this side, then they are both positive, that means their multiplication will again be greater than 0. So when I say that we have identified 2 points x1 and x2 such that f of x1 multiplied by f of x2 less than 0, what we mean that one of this point is on right side of the solution and another point is on the left side of the solution. So for instance, it could be like this: x1 is here and x2 is about here. That means f of x1 is negative, f of x2 is positive. That means f of x1 multiplied by f of x2 is less than 0. We can try different values of x1 and x2, and from that we can get 2 points such that this condition of f of x1, f of x2 less than 0 is satisfied. So we understand that between this x1 and x2, this function will change its sign, which tells us that between these 2 points x1 and x2 there must be a point where f of x equals 0, and that tells us that between these 2 points x1 and x2 we do have a root. Now the question is how we can close this gap of x1 and x2 and reach this root. So we employ a very simple method here, and the method of narrowing the interval of x1, x2 is as follows. First, or we call it iteration 0. In iteration 0, I get the value of x, and superscript within bracket 0 means this is iteration 0. So this is the value of x at iteration 0 is x1 plus x2 divided by 2. So I have taken this x1, this x2, I divide this x1 plus x2 and I divide by 2. So I will get it somewhere in between x1 and x2. I don't know exactly where, but I have just assumed it will be here, and this will be my x0, that is the 0th iteration of x. Now this 0th iteration of x, we'll see that it is on the left side or it is on the right side. If it is on the left side, then what it will do, we'll take that this x1 is not needed anymore. We now know that root will be between this x0 and x2. So what we do, this x0, I set it as my new x1. However, if that does not happen, if x0 falls on the right side, then I know that my root will be between this x0 and x1. In that case, we take this x0 here and we take that as my new x2. Here this arrow, right arrow, means assigning the value of this x0 in x1, or here this assigning the value of this x0 in x2. So in iteration 0, either x1 or x2, one of them will be updated, not both. One of them will remain just the same and one of them will be updated. They will be updated by x1 plus x2 by 2. Now of course we are ready to go to iteration 1, and iteration 1 once again will take this x1 plus x2 by 2. But you can see that now my interval is shorter than what it was before, although they look similar. x0 is x1 plus x2 by 2, x1 is x1 plus x2 by 2. However, one of this has changed. Either x1 or x2 has changed. It has come closer to the root, either on left side or on right side. Therefore, this iteration 1 value of x, we hope that it will be closer toward this root. And this is how we keep on coming closer and closer toward the root. Eventually, of course, we have to stop the iteration and we have to assume that we have come close enough to the root. As you can understand that in numerical method, we never reach exact solution. We can only come closer and closer to it. We have to set a convergence criteria. We also call it stopping criteria, where we'll stop our calculation. To do so, we'll check this x. For every x, we'll check this f x of xk, and when this comes to be very small, the small real number epsilon, that we'll set it according to the accuracy that we need. When fx of xk, absolute value of this is very small, this is close to 0, we will assume that my xk is the acceptable solution. It will still not be equal to the exact solution, but it will be our acceptable solution, and we will stop our calculation there. So let us see an example. So we take a very simple problem. This is x square minus 7x plus 10 equals 0. It's very easy to see that it has an exact solution of x equals 2 and x equals 5. We can use bisection method and try getting one of this solution. In bisection method, we can only get one solution. So between the two intervals, we assume that there is one solution. If there are multiple solutions between the two intervals, we'll only get one of them. So here you see that for x1 equals 0, fx is 10, and for x2 equals 3, fx is minus 2. So we are very sure that between 10 and minus 2, there is a solution fx equals 0. So between 0 and 3, x1 equals 0, it is 10, and x2 equals 3, it is minus 2. So between 0 and 3, there must be a solution fx equals 0 between 0 and 3. So we have a root in this interval 0 and 3. So let us try to find that root. If I keep on calculating it and create a table, I'll get a table like this. So this is my iteration counter, first column. In iteration 0, I have x1 equals 0 and x2 equals 3. So my x is the average of these two, that is 1.5, and f of x is 1.75. Remember that when f of x is close to 0, we'll sort of reach the solution. So now with this x, I update the x1, my x2 remains same. So my x, new x comes 1.5 plus 3 divided by 2, that is 2.25, and f of x comes minus 0.6875. You can see that earlier it was 1.75, now it is 0.6875, so it is coming down. Then I take this 2.25, it is my new x2, my x1 is 1.5, so my x is 1.5 plus 2.25 divided by 2, that is 1.875. f of x is 0.3906. You can see that we are coming down. In this manner, if we continue our calculation, we will see that this x1 and x2 are coming closer and closer. They were initially 0 and 3, which means that in between them we had this root of 2. Now you can see that it is coming 1.5 to 3, 1.5 to 2.25, 1.875 to 2.25, etc., etc. So then you can see that from 7th iteration it is coming 1.99 to 2.01 in that range, and it is still coming down. In 10th iteration it is 1.9980. There will be difference between 9th and 10th in more significant digits if we take, but for simplicity I have removed those digits in the table. So you can see that within 10 iteration it comes down to 1.9980, 2.0009. My x is 1.9995. We know exactly the x is 2. It is coming 1.9995. And f of x is 0.0015. It is small, but it is still not very close to 0. So we keep on iterating it, and we can see that my fx is coming down closer and closer to 0, and my x is coming closer and closer to 2. So we are convinced that we are going in right direction, and more iteration will give us the acceptable value of the root. Our iteration will stop when the value of this fx is less than this epsilon, which we can define depending upon the accuracy that we want to have. One of the major advantage of bisection method that it will always converge to the root, and that is a huge advantage in any engineering application. So let us take that we are starting from this interval x1 and x2, and this 0 indicates their 0th value. So initial value of x1 and x2, which means that it is their 0th iteration. We'll now iteratively update this x1 and x2. When we update this x1 and x2, we go to first iteration. We know that one of them will remain same and one of them will be replaced by the average of previous iteration. So in iteration 1, x1 1 may remain same and x2 may be updated using the average of previous iteration x1 and x2. So it is either this, or it could be so that x2 remains same as the previous iteration value and x1 is updated with the average of x1 and x2 from previous iteration. So one of this will happen after the iteration 1. Then we see that the difference between x1 and x2 after iteration 1 is, any way I take it, I see from both sides, this is x1 0 minus x2 0 by 2, or what we can say that iteration 1, the difference between x1 and x2 is equal to the difference between x1 and x2 at iteration 0 divided by 2. So their difference is decreasing, which means x1 and x2 are coming closer and closer. Similarly, after iteration 2, what we will have is that x2, that means x1 in second iteration, x2 in second iteration, their difference equals x1 in first iteration, x2 in first iteration, their difference divided by 2. Now we know that x1 minus x2 in first iteration equals x1 minus x2 in 0th iteration divided by 2. So I can write that this is equal to x1 minus x2 in 0th iteration divided by 2 square, taking help from here. If we proceed this way, we can say that after kth iteration, my x1 minus x2 will be x1 minus x2 at 0th iteration divided by 2 to the power k, which means for large value of k, the difference between x1 minus x2 will be very, very small. In other sense that limit k tends to infinity, their difference will be 0. So if I have infinite iteration, this x1 and x2 will fall exactly over one another, but we are not going through infinite iteration, but increasing the value of k gives us closer and closer range of x1, x2. So limit k tends to infinity, x1k minus x2k equals 0. Therefore, we can say that bisection method will always converge to correct solution. Of course, to reach the correct solution, it may require large number of iteration. Here what you see is a pseudocode for bisection method. We have not discussed pseudocode yet. It is coming in next week. So don't worry about it if you don't know what it is. But essentially, this is a computer program written in our own language. This will not run in a computer. This is for our own understanding. Here, this is the input. Input is f of x, x1 and x2, where f of x1 multiplied by f of x2 is less than 0. And we are also giving an input of this maximum error, which is the epsilon or the stopping criteria. The final result will be x naught, where f of x naught is less than this maximum error or epsilon. So here you can see that I get this y1 and y2 at this x1 and x2, and as long as this is less than 0, I'll go through this calculation. If it is not less than 0, I'll simply print that we have invalid input and we'll exit the program. Then we calculate the error. Error will be minimum of this y1 or y2, whatever is minimum. And this, as long as my error is greater than maximum error, then we'll do this calculation. What I have already explained, we'll get this value of x naught is x1 plus x2 by 2. We'll check if this x naught is good enough. If it is not, then we'll replace this x naught. It will be either x1 or x2, and we'll continue this way until the solution converges. Now, to summarize this lecture, we have seen bisection method, the theory, the convergence, as well as an example. It solves one equation for one unknown. It starts from an interval that consists the intended root, and then the goal here is to close the interval iteratively. Using the technique that I have discussed and using simply a handheld calculator, you find one root using bisection method for this equation x square minus 7x plus 7 equals 0. You develop the table as I have shown in this lecture. Hand calculation is enough. You do not have to write a computer program. Even if you can write a computer program, I'll still urge you to do a manual calculation. This will help you to understand how the procedure works. That's all for this lecture. Thank you, and I'll see you in next class.